Um, Thank you, everyone, for including me in this. This is great. This is definitely the most chemistry I've ever consumed as an audience member. For me, the overlap with Jim is more in the scientific aesthetic and approach. So as I'll talk to you a bunch about, my group uses radar to look at ice sheets, which is quite different. But what I share with Jim is that my group builds the instruments we use and does the science and interpretation using their results. So hopefully what I'll leave y'all with at the end of this talk is an interest in ice sheets and hopefully a reasonably functional mental model of radar and an idea of some of the problems we work on with that. So I, like any other glaciologist you'll hear a talk from, my work is motivated by trying to project sea level rise out 100 years out. And so even this range here on the right side, which is ice sheet models, current projections, that range is the difference between displacing like 4 million people on the coast or not. And that's just within current models using current physics we currently observe. But if we look at the geologic past, our current rate of sea level rise is actually low, compared to what the Earth is capable of. And even these steepest slopes here is this dashed line. So we know the Earth is capable of much higher rates of sea level rise, even than our models can project. And so this is one of the problems we try and work on. Part of why it's hard, despite that societal relevance and costly impact, is that the main sensors we have to observe the ice sheets from space all only look at the surface. So whether you're talking about imagery, surface velocities, laser altimetry, that all just measures the surface of the ice sheets. And most of the uncertainty in the processes that govern how ice flow happen on the bottom of the ice sheet, beneath kilometers of ice. And we cannot, at present, and maybe at all, do that from space. So my area of radioglaciology addresses that by using radars that are mounted on airplanes mostly to look through the ice sheet. So this is a DC-3 airplane that fought in the Battle of the Bulge that's been retrofitted to do polar surveying. There's a little antenna there under the airplane. And the way the radars work is they send a pulse down through the ice sheet, they come back, you record them in the antenna. And so all these little blue lines here are individual flight lines flown by different countries over 4 or 5 decades. So this is everything we as humanity have been able to piece together. And the main thing that we do with this is then we grid it up and make maps like this of what the continent would look like without ice sheets on top of it. So that's one thing. We need that. That's what goes into an ice sheet model that then projects sea level. You run how an ice sheet would evolve over that. To give you a sense of what the data looks like, so this is a single flight line from the center of the continent to the edge. You can see the shape there. That's the ice. This is the continent underneath it. So we are seeing through 4 kilometers of ice with the radar, which is amazing. We can see mountains. We can see internal layers here, which are kind of like tree rings or layers of a cake, which are climate records. And then over here's where the ice starts to go afloat. So those are the main ways historically our field has used this data, is either maps of the bottom or cross sections you can look at. Now, you can also look at the strength of the reflection from the radar. So this slide I'll take to hopefully develop your mental model a little bit of how you can interpret this data. So this is a subglacial lake. So here are those layers in the radargram. Again, these are vertical slices downward, right through the ice. And so here is a lake. Here's a mountain to the side. Here's a mountain to the side there. This is a lake. We know it's a lake for like 2 reasons. One is it's flat. It looks flat. We can say, hey, that looks flat. And you can imagine that melting and freezing processes underneath a cap of ice could make something that's flat. In fact, most of the lakes you will have seen under the air are also flat. And then also it's bright. So when the radar comes down, it reflects off of the water. And if maybe you think back to a high school undergraduate physics course, maybe you had a case where you had like a string and your professor wiggled the string and a wave went down and then it like hit the wall and it reflected off the wall, and you attached it to like a string that was just the same and it all went through the string, and then you attached it to a bigger string and like some of it came back and some of it went through, and how much went through or came back, partitions, how much energy goes either way. That like, you're a radioglaciologist now. We're doing the same thing on the bottom. The difference is these reflection coefficients. The more different ice in the ground is, the more or less energy is reflected. So some of these that are near 0 dB mean that basically all the energy comes back. That's like string attached to the wall. And some of these things that are small, like -40 dB, that's like 10 to the -4th, almost none of the energy reflects back. So this is 10,000 times brighter if you have water or not. That is a luxuriously giant signal. And you can imagine sort of, pretty careless analysis can still see something 10,000 times brighter. The downside to that, which is great and attractive, is that the ice absorption also varies with temperature a lot. So not having looked at these before, the main things to look here is this is in units of dB per kilometer. So this is an exponential unit over a linear unit, and then it still looks exponential. And so the point here is the difference as ice gets warm and how much it absorbs goes from like 1 or 2 dB per kilometer, so that's very, very small, all the way up to like 50 dB per kilometer. So that's like 100,000 times more per kilometer. And the reason for this, I was mentioning last night, my dad's an appliance repairman. The way microwaves cook your food is they vibrate water molecules. They're good at that. But when they're frozen as ice, they don't vibrate, very much so. And so as the ice starts to, and you put ice cube in your microwave, it won't melt. You should try it. But as it starts to melt, you get a little water in there and it starts to absorb that energy much more. And the challenge with this, or as I tell my students, the fun, is that there's this ambiguity when you get a reflection of, is it brighter because it's colder and reflecting from the bottom, absorbing less, or is it brighter because it's more reflective on the bottom and reflecting more energy? And separating this is part of the challenge. So with this mental model mostly, you now are sort of situated to look at ice penetrating radar data and interpret some of it. We can actually go through and look at a whole menu of physical processes that govern how ice sheets evolve. So how much snow is on the surface, the crystal fabric of the ice, how much water is in the ice, groundwater beneath it, inglacial and subglacial hydrologic systems, the temperature, active volcanism, melting and freezing beneath the ocean. All of that can be done using the same sort of logic and these same sort of signals I was just showing you on the previous slide. So, okay, well, I'll walk you through a little bit, some of, a few vignettes of how this can be used for areas of Antarctica we care about. There's one glacier, Thwaites Glacier, that gets a lot of attention in the news. Some people call it the Doomsday Glacier, which probably it shouldn't be called, but it is the glacier that is configured most to go away in an unstable way that could spread to the rest of the ice sheet. The sort of logic here is like ice flows, it's like a viscous fluid. You can think of like honey, right? So if I like spread a layer of honey on the table, like it would flow, but not very fast. But if I somehow built like a giant tower of honey, I guess, it would flow quickly because it's thick and there's gravity, right? So now if you have a ice sheet, right? So the thicker it is, it flows, starts throwing icebergs out of the edge. If the bottom is sloped down, then as icebergs go out, it gets thicker, so it flows faster. So more icebergs, so thicker, so faster, so more icebergs. And if it was shaped differently, then that positive feedback wouldn't be there. So Thwaites is a big deal because it's shaped that way. And it's shaped that way all the way into the middle of the ice sheet. So if it was to retreat where it's from, it could spread to the entire Western Arctic ice sheet. And this is the way we think we can get some of those big numbers that our models don't currently project. It's such a big deal that there was a whole proposal jointly funded by the US and the UK. You could only study Thwaites, and there were teams. And they had acronyms like Dominoes and GHOST. And then there's one that didn't have an acronym, this boat project, but then they felt left out, so now they're called Thor. And then I'm involved with Time, which competes with GHOST. And it's great because it's an important glacier, but I'm not sure that we should focus so incredibly narrowly only on this one glacier. So here is an example. So here's, to help you, here's Thwaites. And then next door, there's this glacier, Pine Island. And so Thwaites is the most changing, most mass-losingest glacier in Antarctica, and next door is Pine Island. And even these velocities here will show where the ice flows, even if you never looked at this. If you think about it, it's a viscous fluid, it's flowing, things, imagine honey or something like that. I would never draw stuff flowing here and then having this sort of weird tumor of ice flow out that way. Like even to first glance, that is weird looking. Right? These blue lines here are models that you can just trust me predict where water underneath the ice sheet would flow. And what's weird with this is from the same region here, the water flows into Thwaites, not Pine Island, right? So that's also super weird. Ice and the water underneath it almost always flow in the same direction. And so given that you have these two really rapidly changing glaciers that are next to each other, that we'd like to understand how they evolve, we don't know why it is shaped like this, and we don't know why the water and ice flow in different directions. And one of the reasons, to go to points Jim has made to me before, is that sometimes with these models,
what you really need is new observational or experimental approaches. And in this case, you can see part of why this is mysterious is these two separate colors are two separate surveys collected with two separate radar systems. So this brown one is a British radar system, operates at a different frequency with a different pulse scheme. This is an American radar system from the University of Texas. They were collected luckily at the same time and luckily with this one reflight line. But part of why we don't know how this part of the glacier works is it's just at the border of these two separate surveys with these two separate systems. So fortunately, my group, which is about half electrical engineers and half geophysicists, had some electrical engineers who were excited, if slightly begrudgingly so, to really cross-calibrate these systems with one reflight, which could then let us make this map of how reflective the bottom is. And you guys now know from our earlier discussion that things are brighter or wetter, things that are less bright are colder and more frozen. And even if this is the first time you've looked at reflectivity of a bottom of a glacier, you can see that this region where the water was supposed to flow and the ice wasn't flowing is blue. And that is blue because it is frozen to the bottom. And even if you haven't spent a lot of time thinking about glaciers before, if you say, okay, the two most rapidly changing glaciers in Antarctica are separated where water flows and where ice flows because a piece of the ice is frozen to the bottom of the bed, of the continent below. Frozen things can thaw, right? And so that means this border between these two important glaciers is potentially pretty ephemeral and dependent on the fact that it's just sort of frozen to the bottom there. And we were able to do that by cross-calibrating these measurements of these instruments. So we're gonna go downstream a little more. So what we were just talking about is sort of up here. These are shear margins. This is where fast-flowing ice is next to slow-flowing ice, right? There's no topographic control. It's frozen in one spot, not in the other. And so this divide here, so you can see this, all these other black lines, so this is topography underneath, all these other black lines are, you could draw them, right? So this is a volcano, the ice is like flowing around the volcano. Here's some high topography, it flows around here, flows around there, all makes sense except this one, right? The same one we were talking about. In this case, the margin flows right above some high topography. And if you look at the radar reflectivity, which you guys are now professional at, you can say, oh, look, it's thawed here where it's flowing fast, and it's not thawed here where it's flowing slow, and that could make sense. But you're still in a little chicken and egg situation. Is it that where it's flowing slow because it's frozen, or because it's flowing slowly, it's not producing heat, and that's why it's not thawed, right? And where it's flowing quickly, is it flowing quickly because the water's lubricating it, or because it's flowing quickly, it produces enough heat to produce water? So this doesn't answer why this boundary is where it is. And so the hypotheses that are out there for why the boundary is where it is are very fine scale things. So one hypothesis is that it's actually warm, that where this ice is flowing past each other is warm and therefore more viscous and therefore easier to deform. And the other is actually the crystal fabric of the ice itself is anisotropic and how strong it is, and actually the fabric of the crystals are both deformed and reinforced where that margin is. So these are both things that we don't have tools currently to observe. So one of my PhD students who's defending now, Nicole, she built a system where you could put a radar transmitter in a stationary spot and then use a software-defined radio, which is used for like, eavesdropping on people in electronic warfare or building self-driving cars, and eavesdropped on our own radar and made it where you could move further and further away so that you could do an image sort of like a CAT scan with more pathways through the ice, and you could constrain where that warm spot is. Another student of mine who had done his PhD, or a postdoc of mine who does PhD on fish optics and how like mantis shrimp use like circularly polarized light to like communicate and fight and mate. So he used those simple fish optics models to make a simple model down here of what ice fabric would look like, and here are the observations. And these observations come from just taking a radar and like spinning around on the surface of the ice to get a different polarimetric response. So these two things, camping on the ice for months at a time and digging tons of snow pits, allow us to then look at these two pretty ephemeral things that may govern the border between the two glaciers. Okay, moving downstream further. So okay, everything we talked about, here's that upper region that maybe is only controlled by freezing. Here's this boundary that's maybe controlled by the temperature in the margin or ice fabric, super subtle stuff. If we go all the way down to the ocean here, we can see red, everything's accelerating except this little spot of blue. And that spot of blue is decelerating because the ice hits the ocean, starts to go afloat, and then there's a piece on the bottom of the continental shelf that the ice is stuck on. And so there's some hope where you could convince yourself, okay, if this spot right between these glaciers is slowing down, maybe it will slow down, maybe the ice will pile up, maybe this can stabilize the system somewhat. And we happen to be incredibly lucky that two modern lines here in purple went over this ice shelf, and then one, the very first and only survey line in this region from the 70s, also crossed right over the ice shelf. So this is, for my field, this is like profound data richness. However, the original data was recorded on 35 millimeter optical film, which were held in a museum archive at the University of Cambridge, the Scott Puller Research Institute. And fortunately, they were willing to let us go and bring this scanner that was meant for retouching old Hollywood movies. And I had two friends who had studied art history who were somehow out of work, and they were willing to come with me. And we spent 2 weeks scanning all these, this film, and we made 2 million images. And just to give you a sense here, so here's the published paper of this piece of film, and here's our high resolution scan. You can even see a piece of masking tape there where they had marked, this is the piece of the film that would go in the Nature paper. And with that, we were able to extract these archival measurements of, in this case, 30 years earlier. And you can see the same ice shelf is here. So, okay, here's a piece of bedrock, it goes afloat here. Here's this piece where it gets stuck. This is what's stabilizing things. And by comparing it with these two modern radarograms, what you can see is the place where it's stabilizing is getting smaller and smaller. And you can see the middle here is getting thinner faster than what you would see on average from satellite. And so this shows that probably in the next, I don't know, 5 years or so, this is likely to melt through and shatter, and it's not going to stabilize it. But again, this comes through a deep understanding of the earlier system and ability to go scan old film data. Also amazingly talented sort of radar engineers after World War II, capable of making something that looks so favorable compared to modern data. My students also are super into citizen science and open data. So actually you can go, if you're so inclined, to radarfilm.studio and play with these 2 million images and all of the blue stuff we've positioned and the gray stuff we haven't. So if you want to spend your evenings and weekends hanging out with friends, helping us position this data, you are most welcome. The other piece, everything I talked to you about so far has been sort of radiometrically looking at it. You know, we spent all this time talking about how bright the reflections were from the wall, and what I showed you just was changing shape. And so the challenge, one of the things I'm most pleased with, is actually trying to take this data and look at it radiometrically. And the challenge with that is people had to compress the brightness in very clever ways to get it to fit on optical film. And the only record we had were these weird 1960s Danish circuit diagrams that I had this amazing student after her first year of undergrad who spent a summer coding up a simulator for that whole circuit diagram, including symbols that are no longer used, and then was able to simulate what the response of a radar we no longer have is. And what we're able to do is, so this is from the film using this response, and here's this brightness, you know, the reflectivity, how bright the water is, and here's modern data. And you can see by going back, understanding the system, resimulating that, we're able to now use this archival film in the same way I was talking about. So it's not like the most celebrated paper, but this is probably the thing I'm proudest of that we've done. Okay, so that was all sort of measuring things now. There's also questions going forward. What will change the system? So we made this big deal about pieces of the bed that are frozen. Well, what happens when they thaw? So I was always interested in a little piece here on the edge of the ice shelf that's frozen. I said, okay, well, what if that thaws? And my student Eliza took a much broader view where she looked at the ice sheet as a whole and categorized it into sort of three things. So, okay, there's a piece where it's frozen to the bed, totally frozen. There's pieces where things are flowing fast, where it's definitely thawed. And she talked about sort of what about like a thawable region, somewhere that's frozen, but just barely so, where you could imagine perturbations actually thawing it. And so she went through and simulated how the ice sheet would evolve as you thawed different thresholds, different temperatures, different regions. And one of the things that came out that was rather amazing is the Thwaites region over here that we were talking about actually isn't that sensitive to thaw. And that makes sense. It's already thawed. That's why it's changing so quickly. There's other regions here like the Disciple Coast, which are in balance. They're very dynamic. They're very beautiful. The ice speeds up and slows down and lakes pump up and down, but it's sort of in an equilibrium where, again, thawing doesn't make a big difference. But there's areas here like Wilkes Land or over here, Enderby Land, that aren't changing currently, but are very sensitive to this thaw. So this is a region we've largely been neglecting as glaciologists, but her results indicate that it's just hanging out, stabilized, maybe just by how cold the bed is. Another control we're not totally, but mostly neglecting is the geology under the ice sheet, very similar to the discussions of the geologic complexity earlier. It is also the case that underneath the ice sheet, there's real geology, there's not just a shape. And we see on the continental shelf where the ice sheet has retreated, areas where there's deformable sediments, it retreats differently than where there's bedrock. Simulations of glaciers retreating over the next 300 years, if you change just the rheology or the mechanical properties of the bottom to be like sediment or bedrock, it either retreats in 300 years or is totally stable where it is. Radar cannot directly measure bed properties, but my former student, Mickey, who's now a professor at the University of Florida, did some beautiful work on geostatistics where you take our sparse data and simulate what shapes would be in between the lines. You can imagine doing that if you were, in this region and you look towards some mountains and said, okay, what's over there? You'd be like, maybe a mountain. If we were in Ohio and I was like, hey, what's over there? No one's guessing it's a mountain, right? So this is just like a machine learning version of that. And so with Mickey's simulations of what the bed would look like, she was able to compare pieces of the continental shelf where we know, because we have boats and we can go sample things, where there's bedrock and sediments, and comparing just geostatistically the shape of the current bed of the ice sheet, she was able to categorize where is bedrock versus where is sediment. And what's most striking here is you see very little of this middle color. So the shape itself is enough to distinguish these things. And so then we can run our ice sheets on a template that's sort of geologically realistic. The other forcing that we're just now starting to appreciate is a more direct climate forcing of just melt season. So you may have seen in the news in 2012, there was this claim that all of Greenland had melted. It was not the case that the whole ice sheet had melted. It was the case that every spot on the surface of the ice sheet was above the melting point that day. And we had this idea that the ice sheets didn't really care about extreme events in that sort of short, like single year or single day type of thing. But what my current PhD student, Riley, found is that actually that extreme melt year, you can actually see this dark layer in the ice of where the water had refrozen and made this impermeable layer. And unlike normal water systems where in the desert water can sort of trickle in, once there's enough water in there it freezes, then a normal melt season that refreezes piles water on top of that and it expands. And so by doing some more sophisticated electromagnetic modeling, he was able to show that the amount of ice there was and how dense that ice was, even in normal years that followed, expanded. So this shows that the surface of the ice sheet is being remade even by sort of single extreme events. Perhaps the most exciting combination is my former postdoc, Winnie, who's now a professor at Georgia Tech, did some very clever analysis where she used an ice sheet model to predict, as you all know now, the warmer ice is, the more it absorbs energy, right? So they used an ice sheet model. She predicted the absorption. There was more absorption than that. She attributed the rest of the absorption to extra water in the ice sheet and was able to reproduce seismic data, which is sort of the gold standard for us of how much water's in there. And so if you take her approach of modeling and looking at the difference and then look at film, which we also scanned right before COVID at the Danish Technical University in Copenhagen, we might be able to say how much water was there in the ice sheet in the 70s versus now, and is this a new process? Okay. Going forward, not just these archival records, we'd like to see these changes, in real time. This is a stationary radar system we use with 8 transmit and 8 receive antennas. We leave it on the surface, bury a bunch of car batteries, it stays out all year. And again, this is the luxury of these stupid big signals, right? Like even if you haven't thought about, radar very much before, this is 50 dB, so that's 10 to the 5th. So the radar got absorbed, and it got weaker and weaker, and it stayed weaker, right? In a giant way. And these colored lines show that that amount of absorption we see is how much absorption you would get if all of the melt on the surface was stored inside the ice sheet instead of flush to the bottom like a toilet, like we typically think. And so what this shows is in some parts of the ice sheet's actually holding on to the water deep into the winter, and that helps explain some of the responses we see that are somewhat confusing, where sometimes you get a lot of melt and the ice sheet speeds up, sometimes you get a lot of melt and it doesn't. And it's probably because the ice sheet is holding on to water inside of it. Also, sometimes you deploy these things and then a crevasse opens up underneath them. And so after my students heroically rescued the radar from over the crevasse, one of our undergrads was able to
spend a whole year correcting a bunch of artifacts from the violence that was done to the radar and see a crevasse opening, which is important for understanding the mechanics of the ice and predicting sort of calving rates. All right, so okay, looking into the future. So that's all now what we've been able to piece together. It's totally reasonable to ask, because we have beautiful radar coverage at Mars, why don't we just put an orbiter up? And I, officially speaking, am on proposals to do this. However, unofficially, I think this is not going to work very well. And the reasons for that is, one, as you now know, ice that is warm absorbs more energy. Earth is much warmer than Mars, and so we need a lot more energy. It's also the case that there's some clutter challenges. I think those are overcomable. There's also the ionosphere, which is worse on Earth. That's also overcomable. The real challenge is we have the FCC on Earth, and we do not have it on Mars or Europa. And as a result, how much we can transmit at what frequency bands is actually a major limiting factor. This is one of the reasons that Jim and I share a great enthusiasm for drone-based surveying, whether we're talking about lower scale drones or drones in the way upper atmosphere. One of the things that you can do is you can use the autonomy and adaptability to survey optimally. So you saw those initial plots. Our lines are very sparse, even in good coverage areas. That means you always have to interpolate. One of the ways you interpolate is you fly a bunch of lines next to each other and you process a swath and it looks beautiful. And sometimes that's the right thing to do. Another thing we do, and I can talk to you if you're interested afterwards about reasons you might not want to conserve mass, which seems like a bold claim, but a means of interpolation people do is you think if you had a valley, right, and ice is flowing into it and you're going to conserve the mass of the ice, if you know how much is flowing in up at the top of the valley, how much is flowing in down below, then you can interpolate between those, and that's pretty good. You don't need a lot of data between there. Or I talked about Mickey's geostatistics. What you can do with a drone, which you can't do with the satellite, is you can have a low or machine learning approximation to an ice sheet model on the drone. It can be flying along and collecting data that maximally reduces the uncertainty in the topography given the interpolation scheme to maximally reduce uncertainty in sea level rise per dollar gallon of fuel, flight hour, whatever. COVID has really hammered my students in their ability to do fieldwork, though they are in Svalbard right now and getting real data. They got a permit to fly on campus, which is maybe the most amazing thing to me. And they've been modifying these drones, building radar antennas to build into the wings. And in the long run, we'll take them and deploy them on the ice sheets. And actually, with the successful test at Svalbard, I think we'll likely go to Antarctica this year. I'll give you a couple other quick flavors. This is an example of seeing groundwater underneath a crater. There's a crater underneath the Greenland ice sheet. There's this little layer of groundwater underneath it. What is remarkable about this is that we're penetrating not just a kilometer of ice, but then also the ground. And there's questions, well, if you can do this underneath an ice sheet, why can't you just go map groundwater elsewhere? Probably in deserts we can, but it turns out that you have to be very lucky, and the crater helps out. You need really fractured rock or really frozen ice with water underneath it, and also you need a radar system that is really wide bandwidth. And this highlights the point, again, that it's not just radars that are better in one dimension, it is radars that are tuned to the problem. This is very exciting right now because actually the debate about whether or not there are lakes on Mars is entirely a radioglaciological debate. You are now all capable of engaging in this debate. Lake on Mars is only because this blue line, reflection from the bottom, is brighter than this red line, reflection from the top. That's it. That's all the evidence we have. And you can choose your mental model for this fight. Either you think there's water, even though it is way colder than we can think salty water can be. So maybe you as chemists can solve this. There's some special way on Mars, cold enough, slow enough, salty enough. Maybe it stays liquid. Maybe you trap the water in ice, cold enough, salty enough, slow enough. It can stay somewhat liquid. Or you think there are clays. And this argument was a paper that was published by someone during COVID ordering clay from like a home improvement or yard landscaping thing, putting it in an Instapot, which is a consumer grade pressure cooker, to then get the water in there and then dumping liquid nitrogen on it and measuring the dielectric response. And so this is a time in planetary science where that is cutting edge science, and this is the coolest my field will ever be. My student Anna is working on a radar that works over a wide range of frequencies that won't have that ambiguity. So if you're not into like personal consumer, cooking supplies, producing your truth, Anna's radar is right up your alley. Also, my former student Sean, who's at the Naval Postgraduate School, is trying to build very low resource radars that use the sun
as a signal that just listen to the sun and do cross correlations with the sun's radio emissions to measure the reflections that way. And both Sean and this amazing 15-year-old who I'm somehow a pen pal with, who is like developing sort of a GPS system for a glacier that you embed little RFID tags in, are all working on sort of miniaturizing these measurements that can put us in a spot to get really data rich and observing things on the ground. So that was a lot. It was very nice of you to be able to let me present what so many of my students have done, especially since, thanks to COVID, it's sort of been like a weird scholarly rapture where like my whole group is gone now, and new people have appeared in their place. But hopefully that's given you enough that something might have sparked your interest, and we could have conversations about that if it did.